Okay, this problem deals with a spring, and it says it takes 180 joules of work to compress a certain spring 0.1 meters. They first want us to find the force constant on the spring. To find the force constant on the spring, one of the things that we need to do is look at how we've done work on this spring. So for letter A, we know that the applied force on the applied force, which then makes the work applied, is equal to positive 180 joules. The work that the spring does then is equal to negative 180 joules, and we define the work that the spring does is negative because it's resisting the applied force. And it doesn't matter whether you are compressing or stretching that spring. Either way will work out really well. For this one, we know that the work of the spring is equal to, new equation here, negative 1/2 k x squared. We're looking for the k value, so we know the work that the spring does is negative 180 joules. We have negative 1/2. We're looking for k, and the compression of the spring is 0.1 meters, and we're going to square that. When you're done, you should end up with a k value equal to 36,000, and the unit for this is a Newton per meter. So we're looking at how much force it takes in order to compress it. For letter B, they want to know, does it take 180 joules, more than 180, or less than 180 joules to compress the spring an additional 0.1 meters. And for this answer, it will be more than 180 joules. The way that you need to look at this one is the work done at part, so we can say by the spring for part A, should be equal to 1/2 of k times the stretch that we originally did squared. If we double that stretch, we're going to call this work at position B. That's 1/2 times k, and do notice I took the negative out just to make this simpler, times 2 times xa, and then we will square that whole thing. At this point, we're going to go ahead and carry the square through, so we have the work at B is equal to 1/2 times k times 4 times xa squared. If we take the 4 and factor it out, put it at the beginning, we end up with the work done, if I stretch at a distance of b, will be equal to 4 times that original amount of work that we had, which is 1/2 kxa, and the x is squared. So you'll notice that's the same as this equation up here. It's just that that extra stretch of 0.1 meters gives you 4 times the amount of work that you have to do for it. And that is the end of that problem.